Today for day 2, we're going to talk about the exponential function, and more specifically, the exponential function y equals e to the x. If you type e in your calculator, it's an irrational number, like pi. It is approximately 2.71 and then runs on forever. So if we go ahead and graph this function, just like we graphed our exponential functions yesterday, we can go ahead and do that by graphing the y-intercept e to the 0, even though it's an irrational number. E to the 0 is still going to be 1. And then when x equals 1, we said e to the first, or just e, would be approximately 2.71. So we have those two, and we know because it's an exponential function, just like we graphed yesterday, we have this horizontal asymptote at y equals 0. So this is the rough sketch of y equals e to the x. Just like the other ones yesterday, that would make our domain negative infinity to positive infinity because it goes left and right forever. The range would be from that asymptote from 0 to infinity. And then we already said the horizontal asymptote is y equals 0, and the intercept we already said was 0, 1. So even though we have that irrational number in there, the properties for graphing exponential function still stays the same. You just have a special number as that base of that exponent. Quick review. We remember that the average rate of change formula would be f of, we can say over, let's be more specific, over an interval from a to b. So we have to have an interval that we're talking about for the average rate of change. The average rate of change over that interval would be f of b minus f of a over the interval b minus a again. So you're plugging those into each function, or that same function, and then dividing it by that the difference of that interval. One thing we do want to talk about here is on the right side, the instantaneous rate of change for the specific exponential function e to the x can be the instantaneous rate of change when x equals a is e to the a. We're going to show this on the back side, but that's a nice little property about this special exponential function that we can use if we're looking at the instantaneous rate of change at a specific point along that curve. For this function, you can actually just plug in whatever x value you're talking about. Moving down, we're going to go ahead and graph this special exponential function. And again, just like we talked about yesterday, we can use transformations. So in this example, we're going to find the domain, range, intercept, and horizontal asymptote, but we're also got to graph it, and we're going to do that using the transformations. So just like we talked about, we can take that base function that we had, make it a dotted line so that we know exactly what we're transforming. This is just e to the x. And what's happening to this function? Well, we have a negative in front. That's our a value. Now remember from yesterday, when that a value is negative, it is being reflected over the x-axis. So all of the points are reflected over the x-axis. And because that is the only transformation occurring here, we can go ahead and graph that one. The horizontal asymptote also reflects, but because it's on y equals 0, or the x-axis, it's going to stay the same. So we have the horizontal asymptote is y equals 0. The y-intercept changed from 0, 1 to 0, negative 1. The domain doesn't change, but the range is now going from a negative infinity up to that horizontal asymptote, which is 0. So make sure you're going least to greatest. For number 2, if you want, go ahead and pause the video if you want to try this one on your own, and then unpause the video, and we're going to go through it. If you want to stick on and just go through it with me, you're welcome to do that as well. So I'm going to go through this again. We already talked about graphing using transformations. So just like the last one, this base function, that dotted line is just the e to the x. That's an x, not a y. So e to the x, we got to transform it. In this case, that is in the exponent. So remember, opposite, this is going to be left 1. And then the exact outside, this is going to be the up 1. So we take each point, we go left 1, up 1. And then we take this one, we go left 1 and up 1. That's not exact. left 1, and up 1. And then just like the points on your curve have to be transformed or translated in this case, so does our horizontal asymptote. So let's get rid of that original one. It was at y equals 0, but since we went up 1, it had to go up 1. Technically, it can go left 1 too, but because it goes on forever left and right, it's not really going left. So we graph this. There's our graph. Looks nice. Our domain, remember, is always going to be negative infinity to infinity. The range, this time because our asymptote went up 1, it's got to go from that asymptote, which is 1, up to positive infinity. The horizontal asymptote we just said was y equals 1. And now, if you think about it, you could probably figure it out. But if we want to just find the y-intercept, e to the 0 for x plus 1, and then plus 1 below, our y-intercept is at 0 for x, comma, e to the 1 plus 1. We'll leave that as exact, but again, e is approximately 2.71, so you can say it's you can say it's 0, comma, approximately 3.71, and so on. But we'd like to be exact where we can, so that's the exact answer we should be providing. On the back, if we take a look at number 3, it's saying on the interval 0 to 1, show the average rate of change of e to the x is about 1.7 times that of 2 to the x. Then we're going to show the functions x squared and 2 to the x have the same average rate of change on the interval 0 to 1. So the first thing we're going to do is we have two functions here. We have the e to the x function, and we have the 2 to the x function. And what we're trying to do is find that average rate of change on the interval 0 to 1. Okay, so we're just going to do that separately, and then we're going to compare them. So as we mentioned, you plug in e to the b, which is e to the 1, minus e to the a, which is e to the 0, over 1 minus 0. Do a little math here. We have e minus e to the 0 is 1 over 1. And then remember, e is approximately 2.71. So we can say that's 2.71 roughly minus 1, which is 1.71. We use an approximation, 1.71 roughly. Now for the second function, we're doing the same interval. So that'd be 2 to the 1 minus 2 to the 0 over 1 minus 0. That's 2 minus 1 over 1, which is 1. And look at that. We just proved that e to the x is about 1.7 times that of 2 to the x over the interval 0 to 1. So we proved that. Now we have to answer the second part of this question, then show that the functions x squared and 2 to the x have the same average rate of change on the same interval. So the good news is we already did this average rate of change on the interval 0 to 1. It's 1. So that means that when we find the average rate of change of x squared, which we're going to do over here, on the interval 0 to 1, we should get the average rate of change to be 1. So if we plug in 1 squared minus 0 squared over 1 minus 0, that's going to be 1 minus 0 over 1, which is 1. And look at that again. Woohoo! They are the same. Awesome. So we just proved that. That was the ratio of all the intervals from, or the average rate of change on the intervals from 0 to 1 of all three of those functions. Awesome. So now number 4, we're going to talk about the instantaneous rate of change. Okay. So we want to find the average rate of change for f of x equals e to the x, and then find the instantaneous rate of change for x equals 2. Now we didn't give you the interval for these ones. So I'm going to go ahead and provide the intervals for you. But at the end, we want to find the instantaneous rate of change for x equals 2. So what I'm going to do is I'm going to kind of lead you guys into this and talking about what instantaneous rate of change is. Remember that the average rate of change between 2 points along a curve is how much is it changing over time. So if we do this, the average rate of change between this point and this point is the slope between those 2 points, right? That's the average rate at which it changes between those 2 points. Well, as I narrow the interval between those 2 points, we're going to start approaching what's called the instantaneous rate of change, where if I get to an interval where these points are right next to each other, then that is almost the instantaneous, it's called the instantaneous rate of change, where it's the rate of change at which the curve is changing at that exact moment in time. So what we want to do here is for this graph, which is e to the x, is we're going to set you up by starting you with the interval 1.9 to 2. And then we're going to look at the average rate of change. So we're talking about the average rate of change here from 1.9 to 2 on this function. And then the average rate of change between 1.99 to 2 and then 1.999 to 2. So what we're going to do after that is we're going to get really specific, and we're going to do the interval 1.99999 to 2 so that we can get an interval that is very close. So that interval has been closing into a certain point like we talked about on that graph. So when I do the average rate of change on the right column, again, what we're showing is e to the 2 minus e to the 1.9 over 2 minus 1.9. Now for these, you're going to need a calculator. So you're just going to go ahead and type these in to your calculator. Make sure you type them in on your own just so that you're aware of how to type them in. But then after you do 2 or 3 of them, you can just write down the ones that I've done. 2, 3. And then the next one. And what you're noticing, even just after the first 3, is we're getting a little bit more specific. If you were typing them on your own, you'd get some more specific. And then when we get the very narrow interval, we're going to have 7.38906. Okay? So again, the more narrow we get this interval to be, the more exact we get on what the instantaneous rate of change for x equals 2 is. Now, what I do want to talk about, though, is remember on the front page, we said that the special exponential function, e to the x, has a nice character trait about it, is that you can find the instantaneous rate of change for any exponential function with e to the x by typing in e to the a, or whatever x value we're trying to find that instantaneous rate of change at. So if we type that in, e to the 2, you're going to get approximately 7.38906, and so on. Well, look at this. The nice thing is, we just proved by making our interval super narrow, it didn't match on the first one, right? But as we made that interval a lot more narrow, we proved that this property does work for that special case. Okay. So one thing I do want to talk about, though, is, however, if we look at this example here, if f of x was just 2 to the x, this isn't that special exponential function we were talking about. It has a base of 2. If we did this one, and we did the same thing, we have to find the instantaneous rate of change by doing 1.9 to 2. So we're looking over the same interval. And then 1.999999246, comma 2. And then if I did that interval, you would find that 2 to the 2 minus 2 to the 1.9 over 2 minus 1.9. If we plug that into our calculator, we would end up with, give me a sec. We would end up with approximately 2.67868. And then if we do the narrow interval that we talked about, right, we got to get a close narrow interval, we would find that the instantaneous rate of change is approaching 2.77 2.77259. Well, if we use the property that we just talked about, well, 2 squared is equal to 4. So this, again, this property doesn't work. Our instantaneous rate of change on this function is approaching 2.77259. And then again, if you narrow that interval, you're going to get a more precise answer. So the nice thing about this special function e to the x is you can use that property of just e to the a to find your instantaneous rate of change. Looking down at the last problem here, number 5, it says we're showing for that function 1 plus a to the x, show that 1 over f of x plus 1 over f of negative x equals 1. Just remember that this property is true. If I have negative x on the inside as the input, that does not equal negative f of x. Okay, so we got to keep that in mind as we're going through this. So all we're going to do here is we're going to plug these in. But remember, when you have f of negative x, it's affecting the exponent, the input value, you're not making the whole function negative. So if we do that, we have 1 over, let's zoom in here, we have 1 over 1 plus a to the x plus 1 over 1 plus a to the negative x, because again, we're plugging in this negative x for our function, and we got to prove that that equals 1. Leave some space there. Now, in order to do this, we're going to work at the left side. It's the more complicated side. So again, what you got to do is we got to get a common denominator. Well, the easiest way to do that here is just multiply each fraction on top and bottom, numerator and denominator, by the other denominator. Because if I do that, we end up with that least common denominator. Now, it seems more complicated, but as we go through this, we're going to notice the numerator for the first one is 1 plus a to the negative x. The numerator for the second one is 1 plus a to the positive x. And then the denominator for the first one, let's go ahead and distribute this out. You get 1 plus a to the x plus a to the negative x. And then the last one here, remember, when you are multiplying two numbers with the same base, our exponent property means that we are going to add the two exponents, right? So a to the negative x times a to the positive x, same base, we add the exponents, that's a to the 0. And the nice thing is, again, because we had the LCDs, they're the exact same. If we go through the same double distribution, we get the same. Well, as we go through this, let's take a look at the numerators. Because we have common denominators, we can add the numerators. So we have 2 plus a to the negative x plus a to the x. And then in the denominator, we just got to simplify these matching denominators. Well, we know a to the 0 equals 1. So we have 1 plus 1, that's 2, plus a to the negative x plus a to the x. And look at that. The numerators and denominators match, so they will cancel out. You're left with 1, and that equals what we're trying to prove. Awesome. So again, as always, just be careful with everything that you're doing. If you're using a calculator, make sure you're typing them in properly. If you have questions, go ahead and reach out to your teacher. Otherwise, go ahead and work on the homework, and good luck.